last class we discussed the principle of operation of a single phase switched mode rectifier, okay, and we found that the essential condition for the circuit to work satisfactorily is that the magnitude of output voltage should be higher than the peak of the input voltage. Why? That is because we found that when I close the switch, current in the inductor increases. Now when I open the switch, current in the inductor should fall, so that when I close it the next cycle, current will again increase, okay. So in this circuit, if you see, when I open the switch, voltage across the inductor is VO1 minus VO, because diode DB is conducting, VO1 minus VOL. So this should be negative. It can happen only when VO1 is higher than V0. The peak value of VO1 is the peak value of Vm itself, because VO1 is held constant and VO1 is continuously changing, is a full wave rectified. So VO should be higher than peak of VO1, okay. I also told you that I will energize the circuit and I will not close the switch S immediately. In other words, I will allow the circuit to attain a steady state. So therefore I said average value of VO1 is equal to average value of V0, because inductor average voltage across inductor is 0. Now in case, assume that I have energized the bridge as t is equal to 0 and I started operating the switch at t is equal to 0 plus. Output capacitor is completely discharged, okay, and we know that capacitor voltage cannot change instantaneously. What will happen? When I am closing the switch, current increases. When I open the switch, in the very first cycle VO is 0, VO1 is positive, so voltage across inductor is still positive, current increases, okay. So therefore if you see, this is current increases. Now when I opening the switch, whatever the stored energy in the inductor is being dumped to the capacitor, capacitor voltage starts building up, okay. Now during transient stage V0 is continuously changing, okay. So and V0 is less than VO1, so di by dt is still positive, it increases, maybe slope will not be the same, So in the second cycle again I am closing the switch, current increases. Now maybe capacitor might have attained some voltage, so when I open the switch, V0 is still less than VO1, current continues to increase but maybe at a different slope, and it's so on, it goes on till V0 becomes higher than Vm. So if I start energizing the switch at t is equal to 0 plus, inductor current, therefore the source current continues to increase, okay, and after some time it attains a steady state, it decreases, and depending upon the control strategy current increases and decreases, okay. So in this circuit, what is the voltage rating of the diode DB and what is the voltage rating of the switch S? We found that when you close the switch, the entire V naught appears across the diode. Okay, if you see in this circuit, when I close the switch, this V naught appears across dB. This potential, this point gets connected to this. So dB should block V naught. Okay. Also, when I open the switch, diode starts conducting. So this V naught appears across S. Therefore, the voltage rating of S and dB should be higher than V naught and not Vm. Okay. What about the switching times? When I close the switch, diode should stop conducting and immediately the current should start flowing through S. And when I open the switch S, immediately diode dB should turn on. Otherwise, we are breaking an inductive circuit, because you open the switch, diode is taking its own time to turn on. So momentarily you are breaking an inductive circuit. So there will be a spike and maybe a device may fail. So in other words, the switching time of S and B should be the same. Otherwise, in other words, dB should be a switching type of diode. Okay. Whereas the rectifier diodes at the input side, the bridge, you can use ordinary rectifying diodes. Okay. So dB should be a switching diode, a fast recovery diode, whereas these four diodes could be of ordinary type or ordinary rectifying types. Okay. The second point that we found was, in a fixed duty cycle control, we kept the switching frequency constant and we kept T on also constant. But IP, the peak value of the inductor or the source current, is proportional to the instantaneous value of VO1. Okay. So we chose the value of D in such a way that the inductor current or source current is just continuous at omega t is equal to pi by 2. That's because at omega t is equal to pi by 2, when I close the switch for a fixed D, it has attained a maximum value, but then at omega t is equal to pi by 2, when I open the switch, decay is very slow, and therefore if the current is just continuous at omega t is equal to pi by 2, it will be definitely be discontinuous in the entire remaining period. Okay. Whereas if we keep the current just continuous at omega t at near the zero crossing, it has attained a very small current, dies down very faster. So if it is just continuous near the zero crossing, it will so happen that in the subsequent switching cycles, inductor current may build up and it may damage the circuit. Okay. So therefore D is chosen in such a way that current is just continuous at omega t is equal to pi by 2. So the peak value of the inductor current is proportional to VO1, so which is nothing but a sinusoid. So source current is approximately sinusoid, has a high frequency components. Now I can use a very small filter to eliminate these high frequency components. Power factor is approximately equal to 1. Okay. If I use a very small filter, source current will be a sinusoid and it is in phase with the input voltage. So the power factor is unity. In other words, this bridge represents a purely resistive load to the source. hence the name resistance emulsion. This I discussed yesterday. So what did we do for the current control? We took a reference sinusoid, a rectified sinusoid, we called it as I reference. We selected upper band and said as IU star, called it as IU star, then a lower band as IL star. We control the inductor current within this band. So when the inductor current touches the lower band, I close the switch, current increases. When it touches the upper band, I will open the switch, current decreases. So current is lying within the hysteresis band. So current is almost a sinusoid, okay. Current looks almost a sinusoid. Smaller the band, current waveform will be more superior, okay. But then smaller the band, it implies that we are switching the device at a much faster rate, okay. So it will so happen that switching frequency increases, losses increases, temperature rise, and therefore a bigger heat sink, okay. But then the source current waveform is superior. So that's whatever you do in life, you have to pay a price. Smaller the band, waveform is superior, inverter efficiency may come down, okay. I have not told you anything about the switching frequency in this case. I will tell you sometime later. Whereas I told you that switching frequency is held constant in fixed D cycle. Nothing I have told you for this scheme. So first we will discuss how to choose this magnitude of IREF, okay. Then we will see what happens to the switching frequency. What is the purpose of this circuit? I told you that I want to keep the output voltage constant. Take any example, get any application. One of the requirement is maintain the output voltage constant. So definitely I need to know what is the actual value of the output voltage. I know what is to be maintained. I have to compare it, okay. That can be done using a simple op amp. So depending upon the error, in other words depending upon the difference between the desired value and the actual value, I need to take a certain corrective action. Now what sort of a corrective action do I need to take? Assume that capacitor voltage remains constant. How constant is that? I will address it after discussing how to determine the magnitude of source current. When the capacitor voltage will remain constant, if there is a perfect balance between the input power and the output power, in other words capacitor does not supply any power or does not receive any power, at that time capacitor voltage will remain constant, okay. In other words, when the input power is equal to the output power, capacitor voltage will remain constant. So if the capacitor voltage increases, what does that indicate? It indicates that source is supplying more power than the required, and in case the capacitor voltage is falling, it implies that the power supplied by the source is less than the required. So what do I need to do? We found that source power factor is unity. So therefore power supplied by the source is V into I. If the capacitor voltage is increasing, you reduce the magnitude of source current, okay. So therefore power supplied by the source to the bridge reduces, and if you find that capacitor voltage is falling, now you need to increase the power supplied by the source, you increase the magnitude of source current. Same thing is true for the fixed duty cycle also. If the capacitor voltage is falling, energy stored in the inductor and being transferred is less maybe, so increase the value of D and vice versa. So here is the loop. I have put a big resistor here, a potential divider. There are other ways to sense the capacitor voltage also. Okay. A very crude method may be a large resistor here, a small voltage I will take. So this is V actual with respect to the negative DC bus. This is a reference value. So this is required given by the application. I'll find out the error, which is nothing but V reference minus V actual. Okay, V reference minus V actual is the error here. I'll give to a controller. Out here I have selected a PI controller. P stands for proportionate, I stands for integral. Okay, PI controller, because I have taken integral action so that at steady state error is 0. Okay, you might have studied this in your control theory. And the PI controller determines the magnitude of Iref or D. Of course, there could be a other block also, maybe a saturator. This is a broad philosophy. Okay, this need not be the actual version here. No, so just a PI controller determining Iref or D need not be true. There may be additional blocks also. So if you find that V actual is higher than Vref, controller may reduce Iref and vice versa. Okay. Now what will happen to the switching frequency in the current control? Assume that there is no load. Okay. Assume if there is no load, source need not supply any power to the output. Theoretical no load, or there is a load, the converter is lightly loaded. So the power supplied by the source is negligibly small. That means I do not need to store the energy in inductor and dump it to the output. I will repeat, there is no load or load is very small. I have charged the capacitor, capacitor voltage is maintained constant there, does not change, no load. So input power should be approximately equal to output power, so it is 0. So I do not need to store any energy in the inductor and dump it to the capacitor. If I do that, capacitor voltage is going to increase. So therefore, ideally there will not be any switchings at all. Ideally there will not be any switchings at all. So switching frequency is approximately 0. And if the load starts increasing now, I have to supply more energy, store it, dump it, store it, dump it. So I have to switch the inductor, therefore switching frequency increases. Therefore, in a current control, switching frequency is a function of load. Remember, in lightly loaded condition, switching frequency may be very low, and as you increase the load, your switching frequency also increases. So what if the switching frequency is increasing or varying, or it is a function of load? I told you that source current is approximately a sinusoid. So to make it a perfect sinusoid, I may have to use a very small filter. Now I can design a filter provided I know the harmonic spectrum. And in all these converters, the thumb rule is that the frequency of the predominant harmonic that is present in the source current depends on the switching frequency. So, as the switching frequency varies, the frequency of the predominant harmonic also changes. So, therefore, how do I design a filter? So, designing a filter becomes difficult because cutoff frequency I have to choose. That cutoff frequency depends on what harmonic I have to eliminate, and that frequency itself is changing. So, in other words, the designing a filter at the input becomes difficult. Also, if I switch it at a very low frequency, it may come down to your audio range and it may produce a noise. Okay. Therefore, it is always desirable to have a constant switching operation. Okay. So, in the current control which I discussed, I chose upper band and a lower band. Frequency is a function of load. There are various techniques reported in the literature to make this frequency constant. I will not go into detail. Maybe if you find time, you read the literature and try to understand. For the first course, it may not be required. But the only thing you remember is that it is possible to keep the switching frequency constant in a current control technique. Okay. Now, coming to the capacitor voltage, will there be any low frequency ripple in the output? Source current is sinusoid. We found that source current is a sinusoid. Source voltage is also a sinusoid. So, therefore, power supplied by the source to the load, that is including the converter and capacitor and load whatever, is pulsating. Single phase power, instantaneous value of V and instantaneous value of I, both are sinusoids. So, the instantaneous value of power is a constant term and pulsating at twice the supply frequency. Okay. Remember, in the single phase case, if both the source current as well as source voltage are sinusoid, single phase power input, instantaneous power is not constant. It has a constant term as well as it has a pulsating component. So, if the power input to the bridge itself is pulsating at twice the supply frequency at 100 Hz in this country, capacitor voltage will also have a second harmonic component. Remember, okay? It has a second harmonic component. So, capacitor voltage will have a second order harmonic component. It is not constant, okay, even if the source current is sinusoid. Okay. Remember, what happens in the three phase case we will see when we discuss the three phase converter. Okay. By the way, I have connected a resistor across the capacitor and I assume that capacitor is supplying load. Please, it need not be. All the circuits that we studied, single phase bridge, three phase bridge, single phase SMR, these are one of the blocks of the various power electronic equipments we will be studying in detail. Okay. In this case, I just connected a resistive load. Okay. These are the building blocks for the various equipments we will be studying in detail. Okay. Remember. In the previous case, in the SMR, we had connected the inductor on the DC side. We rectified the AC, then in between the bridge and the switch, we connected an inductor. Now we can shift that inductor to the source side. Operation of the circuit is the same. Okay, operation of the circuit is the same. So when I close the switch, in the positive half, you have D1 conducting, switch D2 conducting. Okay, and when I open the switch, inductor current flows through D1, diode DB, load and D2 back in the positive half. In the negative half, D3 and D4 will conduct the carrier. But then what is the difference? There is no difference in the working principle of the circuit. Only difference is that now inductor is in the AC side, current that is carrying is alternating. If I put the inductor on the DC side, it is a full wave rectified current. So therefore, we are not utilizing the iron very efficiently, because only half of the BH loop we are utilizing. Current increasing, decreasing is always positive. BH loop or BH, if I plot B versus H, we are always in the first quadrant. Whereas in the second case, when the inductor is on the AC side, we are using the both halves. In other words, a better utilization of iron is possible. Okay, so that is only the advantage. Maybe. Okay, we will see the next circuit. Same in the sense, recall our AC to DC conversion. Initially we had all 4 diodes under switch. Now we replace 2 diodes by 2 self commutating switches, S2, S4, D1 and D3 are the diodes. Okay, how does this circuit work? Same. In the positive half, I will close S4 only, close S4 only. So what will happen? Source, inductor, there is a short here, and D2. Okay, D2. So here is the equivalent circuit, L, S4, D2. So in other words, inductor is short circuited, Vi, this voltage is proportional to the instantaneous value of Vi, it could be negative also in this case. Capacitor is supplying power, the conditions are the same, output voltage should be higher than the peak of the input. Okay. After some time, depending upon the control strategy, either whether it is a fixed duty cycle or a current control or any other control strategy, when I open S, what will happen? Inductor current was flowing in this direction. When I close the switch, it will try to flow through D1, capacitor, load, back to source to D2. Okay, the circuit. Stored energy in the inductor is transferred to the output. So operation is the same. So in the second half or in the negative half, I will close S2. So current will flow. Now potential of B is higher than A in the negative half, flow through S2, D4, L, back to source. S2 D4 inductor back to source. Okay. This is the equivalent circuit. When I open the switch S2, current was flowing in this direction. So what will happen? You have opened the switch. So there is a diode in the upper half, D3 load, D4 back to source. Okay, to source. Source D3 load D4 back to source. Same thing, same principle. IL decreases provided value of Vm is less than V0 or Vi is less than V0. When I open the switch, current decreases. Principle of the operation is the same. Okay. I have a question to ask. What sort of a waveform will you observe at the input side of the bridge? What sort of a waveform? At one side you have pure sinusoid. We are assuming that source is an ideal sinusoid, an inductor, and we are connecting to a bridge. What sort of a waveform will I get when S4, S2 are continuously switched? Okay, will it be a sinusoid or will it be a step wave? See, in the previous transparency, when I closed in the positive of course input is still a sinusoid, voltage across AB or VAB is 0. This is A, this is B. VAB is 0. Okay. See, S4 and D2 are conducting. This is V, this is point A, this is point B. So they are connected together. There is a short circuit. So VAB is 0. Okay. And when I open the switch, this is A point and this is B. B is at the negative potential of the capacitor voltage, and D1 or point A is at the positive plate. So VAB is the capacitor voltage V0. Okay, remember. So when I close S4, VAB is 0, and when I open S4, VAB is V0. Okay. So therefore, please don't say that voltage across VAB is also a sinusoid. No, voltage across the points AB or voltage across this inductor at this point is a stepped wave. In the positive, when I close S4, it is 0, and when I open S4, it is V0. Okay. So I will get a pulses, series of pulses. Switch on, switch off, switch on, switch off. Similarly, in the negative off. Okay. Remember, I will use this waveform sometime later. Okay. Voltage across AB or voltage at the other terminals of the inductor is not a sinusoid. Input is a sinusoid, other side is not a sinusoid. Yeah, similar to the line commutated converter that we studied, uncontrolled bridge, then we studied off controlled bridge. Both are single quadrant, current is also positive, unidirectional, voltage also unidirectional. Then we replaced all 4 diodes in uncontrolled bridge by 4 SCRs. Then we found that voltage polarities of V naught can change, therefore we call it as a 2 quadrant converter. Okay. Similar operation should be possible even in the devices with self-commutating devices, bridge with self-commutating devices. See, in this bridge we have all 4 self-commutating switches. Okay. We have connected a capacitor here, therefore polarities of V naught cannot change. Okay. Polarities of V naught cannot change. Can I change in this link? Yes, I can change, because see, current can flow through this diodes, back and capacitor, one direction of current, and current can also reverse and it can flow through either S3 like this or S4. Similarly, there are paths down also. Okay. By the way, I hope all of you know, if it is like this and if I close the switch, current flows in this direction, remember. See, S4, if I close like this, current will flow in this fashion, downwards. Here also current is downwards. In case if I have this point here in this fashion, if I show it in this fashion, when I close it, current will go up, current will flow in this direction. So there is a sign convention. Okay. So therefore, this bridge V naught cannot change its polarities. Okay. We have a large capacitor here, whereas current can change. I can have a bidirectional current, hence the name 2 quadrant converter. Same thing in a fully controlled bridge, voltage can change, current cannot change, whereas here current can change, voltage cannot change. Okay. Let us see how it works. Okay. First cycle, case 1, first cycle, positive off, depending upon the control strategy, you close S4. Okay. S4 only. So what happens? So in this bridge, I close S4 only, current will flow through S4 D2 back, as in the previous case. Okay. Capacitor supplies power to the load. So the equivalent circuit is here, S4 D2 back and capacitor. di by dt is Vi by L. Vi is the instantaneous value of the input voltage. And what is VAB? Is 0. VAB is 0 because it is short circuited. After some time, again depending upon the control strategy, open S4. Don't need to do anything to S1. Don't have to do anything to S1. We know that inductor current is should be continuous. It was flowing in this fashion, but then there is upwards, there is D1. So current will flow through D1. Current will flow through D1. So even if you try to close S1 here, sorry, even if I close S1 here, current was flowing in this direction. Even if I close S1, current will not flow through S1, current will flow through D1. Okay. D1 capacitor, D2 back to the source. Okay. Okay. So even the same thing in the second half, close S2 only. Okay. Circuit will be completed through S2 D4 inductor, open S2, current was flowing in this direction, flow through D3, load and back. Here VAB is 0, whereas here VAB is minus V0 in the negative of. Please, A is connected here, B is connected there, this point. So VAB is negative, whereas in the previous case, in the positive of, VAB is nothing but VO itself. Okay. So case 1, in the positive of we controlled S4, and in the negative of we controlled S2. Okay. So the waveforms is 0 when the switch is on, and when the switch is off it is V0. Okay. By the way, this pulse is, the width of the pulse depends on again the control strategy. Okay. If it is a current control, maybe pulse width will be continuously change. So I will draw an equivalent circuit. This is the input voltage, inductor, and at this point we found that voltage waveform is a stepped wave. Okay. Definitely it will have a fundamental component whose frequency is same as the supply frequency, and a higher frequency component. Okay. See, let me recall, if the input is sinusoid, current is a sinusoid, we have assumed that current has approximately sinusoid and has a high frequency component. So this voltage also should be a sinusoid having a high frequency component. Okay. So for analysis purpose, I will just use the fundamental component, which is a sinusoid. Okay. So I have a very interesting case here. Input voltage Vi sinusoid, VAB1 is again a sinusoid connected by an inductor L. Okay. Now what is the power that is transferred from source A to B? Or if there is a Vi and there is a VAB, our two voltage sources are connected by an inductor. So expression for power is given by V1 V2 divided by Xs into sine delta. Remember, I think you might have derived this expression in synchronous machine. We have a generator and we have a grid, okay, and interconnected by an inductor. We said that power transferred to the grid is V1 V2 divided by Xs into sine delta, where delta is the angle between V1 and V2. So similarly here, power that is transferred from Vi, the source Vi, to the load, it is Vi VAB sine of the angle between Vi and VAB divided by X or omega L. Okay. Okay. It is this expression, Vi into VAB divided by omega L in sine delta. Omega is 2 pi f. F is the frequency of Vi, the fundamental frequency, 50 hertz. This kind. So depending upon the power rating or depending upon the power requirement, I need to change the delta. I need to just change this delta. Okay. I need to just change this delta. As delta increases towards 90 degrees, power transfer also increases towards 90 degrees. Now what if I make delta is equal to 0? In ideal condition, consider my inverter is a lossless, okay, inverter is lossless, and I have a capacitor at the output. If I make delta is equal to 0, the power expression says that power transferred from the source to the load is 0. Okay. So therefore definitely there has to be no load also in the output. I have neglected the losses in the converter. In other words, converter is ideal, efficiency is 100%. But then power transferred may be 0, but then if the magnitude of Vi and VAB, if they are not the same, current has to flow and current will flow. I will repeat, I have made delta is equal to 0. In other words, Vi and VAB are in phase, okay. Vi and VAB are in phase. If they are in phase and magnitudes are also same, then there is no current through the inductor, okay, because both the potential at both points are at the same potential. They are in phase, but then the magnitudes are not the same. There has to be some current flowing through the inductor, and current will flow. What sort of a current? What is the angle between now the inductor current and the supply voltage? See, the vector diagram for a finite delta is here, Vi, and I want the source power factor to be unity, source power factor to be unity. So Vi Is, Vi into Is into cos of the angle between Vi and the Is is the power transferred, that is nothing but V into I, RMS value of both the system. But then that power is same as Vi VAB divided by omega L into sin delta. So I need to have some angle between the positive zero crossing of the input voltage and the positive zero crossing of VAB voltage at this point, okay. So as you increase this delta, power transferred from source to the load increases. So for this circuit, there is the vector diagram. So VAB plus Is into omega L is Vi, okay, Vi. Now if I make delta is equal to 0 and Vi, the magnitude of Vi is not the same at VAB, and delta is equal to 0, they are in phase, zero crossing of Vi matches with the zero crossing of VAB, magnitudes are not the same, they are in phase, some current has to flow. What sort of a current now? Case, take for example, if the magnitude of Vs is less than the magnitude of VAB, okay. I have not told you how to change the magnitude of VAB. Now assume that magnitude of VAB is higher than Vs, but I have told you that magnitude of VO, that output voltage, should be higher than the peak value of Vm, that I have told you, okay. So in this vector diagram, magnitude of Vs is less than magnitude of VAB. So therefore voltage drop across the inductor should be in this direction, okay. So difference between Vs and VAB should be Is into omega L. If this is the voltage drop across the inductor, current should lag this vector by 90 degrees, okay. So current vector will be in this direction, okay. So now what is the angle between the source voltage and the source current? It is 90 degrees, and source current is leading the source voltage by 90 degrees, Okay. So this is nothing but source feeding a capacitor, or a capacitor is connected across the source. Capacitor current is leading the voltage by 90 degrees. Now take a second case, magnitude of VAB is less than the source voltage. Okay. So this should be Is into omega L. Okay. If this is the voltage across the inductor, current vector, current flowing through should be lagging this vector by 90 degrees. So this is Is vector. Okay. Now we will find that angle between Is and Vs is 90 degrees, and Is is lagging Vs by 90. So this is nothing but an inductor. Okay. So we found that if magnitude of VAB is higher than Vs and they are in phase, source does not supply any power to the converter, and the current drawn by the converter is leading by 90 degrees. In other words, we are connecting a capacitor across the load, across the source. In the second case, if the magnitude of VAB is less than the source voltage, angle between the source voltage and source current is 90 degrees. Source does not supply any power to the load, because we can prove it. Vs into Is, cos of the angle between them is the active power transfer to the load. In this case it becomes, angle is 90, therefore it is 0, and we found that angle between the current and the source voltage is 90 degrees lagging. It is equivalent to an inductor is connected across the source, or source is feeding an inductor. So we discussed three cases. The first case is, I can have a unity power factor operation. The source voltage and source current are in phase. The second is, angle between the source voltage and source current can be 90 degrees leading, and third is 90 degrees lagging. So all three possible cases we discussed. One is, if I can have unity power factor operation, it becomes a purely resistive load. If the angle between them, source voltage and source current is 90 degree lagging, then it becomes a purely an inductive load, and the source current is leading the source voltage by 90 degrees, it becomes source feeding a purely capacitive load. Okay. So unity power factor operation plus or minus 90 degree operation are possible. What are the uses in power system? We will see in our next lecture. Thank you.